Welcome to Calc 36. Today we're going to be talking about logistic growth and using that differential equation to help us model populations. So we're given this problem, well, not necessarily a problem, but the statement that in 1985 and 1987, the Michigan Department of Natural Resources airlifted 61 moose from the Algonquin Park in Ontario to Marquette County in the Upper Peninsula. It was originally hoped that the population would reach carrying capacity in about 25 years. So this is a really nice introduction into my logistic growth problem. And so here we are dealing with moose first off, and we're dealing with a moose population. Obviously wasn't doing too well, and now they're trying to kind of re-stimulate that population. And it tells us it wants it to reach a carrying capacity in about 25 years. So these are kind of the key things that stand out to me when we're dealing with a logistic growth problem. And logistic growth just refers to basically population, not H. And H isn't there. Population. So that's really what we talk about when we talk about logistic growth. And the other word that kind of stood out to me was carrying capacity. And that's just basically the max number of whatever I can have before I can't hold anymore. And so obviously the Upper Peninsula won't be able to hold you know, 1 million moose, and so at some point the population is going to start growing because there won't be enough food to supply for everyone. So that's that carrying capacity. That's that max number that the population can hold without kind of destroying itself. So this is a really good problem to start with. We're given that the growth rate is defined as dp dt equals 0.0003p times 1,000 minus p. And so this is basically what we are going to see for our population growth, for our logistic model. We are generally going to see dp dt equals kp minus m minus p. And k we've seen before, that's our rate of growth. That's just how fast our population is growing. And then m, this is our carrying capacity. This is how many in this case, moose, the population can hold. And so part of this is just going to be recognizing those different things. So the first question is just asking, what is our carrying capacity? I need to make sure that it's in this form where the p is kind of on the outside of the equation in order to find my carrying capacity. And it turns out this one's really easy. My carrying capacity is 1,000. Part B, I'm going to kind of let you guys try on your own because we need to practice our slope fields. But basically, when we plug in our values, since it only depends on p, my t axis is not really going to matter as much. And so when I plug in t for my lower numbers, I get a super gentle slope. It's not very steep at all. And then I start plugging in larger p values and I get steeper slopes. I keep going. And then at some point when I plug in p, my slopes are going to start kind of evening out again. So they're going to start getting less steep. And then we're just going to hit at that carrying capacity. So when we plug in 1,000, this is all of our equation is going to 0. And so we're not going to be, it's just going to be a slope of 0. And so we can kind of see that our graph is looking something like this. Here we go. So what's happening is I'm starting off slow and then I'm growing really, really fast, and then I'm kind of evening out once I get closer to that carrying capacity. So that is just a general kind of slope that we will see when it comes to logistic models. Now part C wants us to solve the differential equation with the initial condition P of 0 equals 61. And so for logistic formulas, or for logistic growth differential equations, we actually have a very nice formula in order to find the integral. So when we integrate this formula, we will always end up with P equals M over 1 plus A times e to the negative m k t. And so A, that's our constant. That's what we're looking for when we plug in all of our values. So using this formula, I'm actually just going to keep it on this page. So I'm given P of 0 equals 61. And again, we're given dt equals 0.0003 P times 1,000 minus P. So I know M, I know T, I know K, I know P, because I'm given P of 0, 61. So what I'm going to do is I'm just going to plug those in to solve for my A, that constant value, because I want to get a solution with A in it. So this looks like 61 equals 1,000 over A times e to the 1,000 times 0.003 times t is 0. And so if you want to try to solve this out, you can. Otherwise, you can just go with my calculation that A is 15.393. And I promise you I'm not lying. And so our equation for when we take the derivative, or when we take the integral, ends up being 1,000 over 1 plus 15.393 e to the negative, t is going to stay my variable, and then when I take 1,000 times 0.003, I should end up with 0.3t. And so this is for part C. This is my solved out differential equation. So here's a DIY problem for you to try if you feel like it. I'm going to kind of walk through the solutions a little bit more than I do on normal DIY problems. So it gives me that the growth population P of bears in a newly established wildlife preserve is modeled by the differential equation dp dt equals 0.008 P times 100 minus P, and T is years. And so it's wondering what is the carrying capacity for bears in this wildlife preserve. B, what is the bear population when the population is growing the fastest? And C, what is the rate of change of the population when it is growing the fastest? So go ahead, I'm going to pause the video, see how much you can get for this one. This one's a little bit different than the one we did before. So I'm going to write down the answers and then kind of go through the solutions with you. So the answer for A is 100. That's pretty easy. We get that straight away from our equation. And then part B should be 50 years. The population is growing fastest 50 years. And then C, the rate of change is 20 bears per year at that 50-year mark. And so I want to kind of go through the last two a little bit. And so when we're looking at our equation, if I were to kind of multiply this out, right, I would get 0.8p, or just distribute 0.8p minus, not equals, oh my goodness, 8p minus 0.008p squared. And so when I'm looking for when I want the population to be the fastest, right, it's going to be when my p squared is maximized. And so when I take p times p, that's going to be the maximum number it possibly can be. And so when we're thinking about squares, we can test a few numbers. And so let's say we had p was 20, and so 100 minus p would be 80. And this product, 20 times 80, gives me 1,600. And as I go up, if I choose 40, So 100 minus 40 is 60. We get 40 times 60 is 2,400. And so this product is going to maximize when my values are the same. And so when I have basically half of my carrying capacity. And so that's kind of important to note, is this is growing fastest at the half of carrying capacity. And that's going to be true for all logistic models. And so for the rate of change, once we find the maximum when it's growing the fastest, all we need to do is plug this into our formula. 0.008 times 50 times 100 minus 50. And that should get us 20 bears per year. So here are your ABC problems for you to try. When it comes to logistic growth, this kind of stuff we just have to keep practicing. It's the same idea, just in different contexts. So I want to kind of give you a few different problems to try. So first we're given the logistic equation, and then we're asked to find the carrying capacity, the size of the population when it's growing the fastest, and the rate at which the population is growing when it is growing the fastest. B, we're asked to solve the initial value problem and then generate a slope field and verify that the slope field conforms, or that our solution conforms to the slope field. And here we're given a population of rabbits, and we're given a formula for their growth. It should be 4.8 minus 0.7t. That kind of was getting a little smudged there. And then we're asked to show that the function is the solution of a logistic differential equation. So we're asked to find k and the carrying capacity. And then we're asked to estimate p sub 0 and explain its meaning in the context of the problem. So go ahead, pause the video, see if you can get any one of these three problems, and then make sure to note which problems you're able to get and kind of where you're stuck. So I'm going to go ahead and put the solutions up. So here are the answers. For A, we should get 200, 160. For B, you should get something that looks like this slope field, and you didn't have to use partial fractions to do this, but you should get P equals 200 divided by 1 plus 24e to the negative 1.2t. And for part C, you're given K equals 0.007, and M equals 1,000. And part B, P of 0 is about 8, and that means there are initially about 8 rabbits. So these are your answers again. Please make sure that you're taking note of where you're at and specifically what you need help with. And make sure to come to class with any questions that you may have. And thank you for watching, and make sure to like and subscribe.